A 50-kilogram man stands on a scale inside an elevator. State the scale measurement for the following cases. Okay, let's begin with the first one, letter A. The elevator moves at a constant speed upward. Well, first what we'll do is we'll write down the information that we're given. We're given that the man
has a mass
50 kilograms as shown here. Now, we need to state the scale measurement. The scale measurement is really talking about the normal force. So that is our unknown that we're looking for. Okay, and the problem states that the elevator is moving at constant speed upward. Okay, so we know that constant speed means the acceleration is equal to 0. Let's proceed by drawing a free body diagram. Okay, we draw our dot. We know that weight is acting down, so that is mg, and we have the normal force acting up. We also know that the acceleration is equal to 0, therefore the forces up should be equal to the forces down, but let's use Newton's second law to make sure that's true. Let's assume that up is positive. Sigma F equals ma. We know a is equal to 0, so ma is equal to 0, so sigma F equals 0. Next, we can look at the free body diagram and take all the positive vectors and add them to all the negative force vectors. We have a positive Fn, and we have a negative mg, and that is equal to 0. Okay, well, let's add mg to both sides. Fn is equal to mg. We have Fn by itself. Now all we need to do is substitute numbers in. We're given that the mass was 50 kilograms, and we know that g is equal to 9.8 meters per second squared. Okay. Okay, if we do that multiplication, we come out with 490 newtons. Okay, so here the normal force was just simply equal to mg when the acceleration was 0. Okay, let's proceed to part B. Part B, the elevator moves at a constant speed downward. Well, again, it's constant speed. It doesn't matter which direction we're moving if we're in constant speed because a is equal to 0. Therefore, nothing changes in this problem. Our free body diagram remains the same. We have normal force up, we have mg down, and a is equal to 0. So we should find that Fn is still equal to mg, which was equal to 490 newtons. Moving on to part C. The elevator accelerates upward at a rate of 1.4 meters per second squared. Okay, now this is a change. We have an acceleration of 1.4 meters per second squared. Let's add that to the data we already have. We have the 50 kilograms, and we know we're looking for the normal force. Okay, let's draw a free body diagram again. We have normal force up, and we have mg down. Now, this time, we should see that the normal force is bigger than mg since our acceleration is up, and if we have an acceleration up, we know that our net force is also going to be up. All right, let's use Newton's second law. Sigma F equals ma. Okay, on the sigma F side, we have a positive Fn since Fn is pointing up, and we have a negative mg since mg is pointing down, and we're assuming up is positive and down is negative. Now, in terms of the acceleration is also pointing up, so that's a positive acceleration, which means this is m times positive a. Okay, we need to solve for the normal force. That means we have to move mg to the other side. So let's move mg. Fn would be equal to ma plus mg, since we need to add mg to both sides. We're now in position to substitute all of our numbers in. Let's give that a go. Fn will be equal to 50 kilograms times an acceleration of 1.4 meters per second squared plus 50 kilograms times 9.8 meters per second squared, since we know g is equal to 9.8 on Earth. Okay, if we do the operations listed here, we should find that the normal force is equal to 560 newtons. This should make sense because our normal force should be bigger as compared to when we're moving at constant speed. Okay, let's move on to the last part of the problem. The elevator accelerates downward at a rate of 1.4 meters per second squared. Again, the acceleration is 1.4 meters per second squared, but the direction has changed. So we're going to see something a little bit different when we draw our diagram. Okay, here are our givens once again. Now let's draw that diagram. We have mg pointing down, and we have normal force up. But this time, because we're accelerating downward, our net force must be downward, and therefore that vector must be a little bit longer. So mg is a little bit bigger this time than the normal force. We don't know how much bigger, but we're going to calculate that. But the last part we need to add is the acceleration, which is pointing down. Now let's use Newton's second law. Sigma F equals ma. We have a positive normal force. We have a negative mg. And then, very important to find this, the acceleration is also pointing down, which means the acceleration will be negative. So we have m times negative a, which I like to rewrite that immediately as negative ma, pulling that negative sign out to the front of the term. Okay, we have to get the normal force alone. So we're going to have to add mg to both sides. If we do that, we'll find that mg minus ma is equal to the normal force. Now it's time to substitute our numbers once again. Normal force will be equal to 50 kilograms times 9.8 meters per second squared minus 50 kilograms times 1.4 meters per second squared. When you run this through, you find out that the normal force is equal to 420 newtons. This also makes sense compared to the constant speed scenario, since your normal force is less than your actual weight, since you're going downward this time, accelerating downward. Okay, that's it.